Hi everybody, welcome back to Advanced Algebra 2. Today we are going to be looking at a new chapter, chapter 4, and we're going back to volume 1 in your workbook. So we're going to be looking at something called inverse variation and then also something else called the reciprocal function, and then we'll see how they're all related. So how are they related and how do we represent them? So first of all, let's talk about inverse variation. I think it helps to understand it if we think about a scenario. So let's say that the scenario is that you want a new MacBook Pro, but the one you want cost $1,500. And your parents aren't going to give you $1,500. I'm not going to give you $1,500, and you have $0 right now. So you're going to have to find a job, and you're going to have to make $1,500 total. So we want to make $1,500. The way you get paid is you make an hourly wage and you multiply it by the number of hours worked. Now, different jobs make different wages. It all depends on what the job is, how much you make, and then how many hours you would have to work. So let's make a table of different possible combinations for numbers of hours worked and the hourly wage to explore what's happening. So we've got 3 columns. One column is for total pay, another for hours worked, and another for hourly wage. Now we want to make $1,500. So this whole column, every single time, I want that to be green, $1,500. That's how much my MacBook costs. That's how much money I want to make. Then we're going to look for different possible combinations for the number of hours worked and the hourly wage I would need if I worked those hours. So let's say I only wanted to do 1 hour of work. Well, if I work 1 hour, then that means I'm going to need to make $1,500 an hour. Now, personally, I don't make $1,500 an hour, so maybe you're going to have to work a little bit more. So let's see what would happen if you worked maybe 10 hours, or then if you worked 50 hours, I don't know, maybe 75 hours, 100 hours, maybe even 200. It's a lot of hours, but let's see how much we would have to make. Now, I'm not going to tell you what operation I'm doing right now, but maybe you can go ahead and figure it out, and then we'll talk about it. I'll give you it eventually, but for right now, see if you can figure this out as we're working through. All right, so if I needed $1,500, but I only wanted to work 10 hours, then I would have to make $150 an hour. If I wanted to work 50 hours, then I would need to make $30 an hour. If I wanted to work for 75 hours, then I would need to make $20 an hour. If I wanted to work for 100 hours, then I would need to make $15 an hour. And then if I wanted to work 200 hours, which is a lot, but you really want this MacBook Pro, then I would need to make $7.50 every hour. So this table just shows not all of them, but several different possibilities for the hours worked and the hourly wage I would need to make in order to earn $1,500 total. Well, what we have done here is we've actually made an inverse variation situation. Notice that the hours worked increase, right? As the hours worked increase, what happens to the hourly wage? It's decreasing. So as the hours worked increases, the hourly wage decreases, but it follows a pattern, and that pattern is proportionally. Because to get the hourly wage, I just took the total pay, I divided it by the hours worked, and that gave me the hourly wage. So that proportionally, it's decreasing because the total pay has to stay constant the whole time. So then if I think about this algebraically, originally I gave you a formula that the total pay equals the hours worked times the hourly wage. Well, I can solve for the hourly wage by dividing both sides by hours worked. So I can say hourly wage is equal to the total pay divided by the hours worked. And in this case, total pay stayed constant the whole time. So I could replace that total pay with a constant. I could replace it with 1,400. And this setup, this something equals a constant over a variable. So a variable equals a constant over a variable. That's an example of an inverse variation relationship where something stays constant. The other two things are multiplied together and it equals the constant. So formally, here's what we can define inverse variation to be. When a relationship between x and y is an inverse variation, we say that x varies inversely as y. An inverse variation is modeled by, and you get three different options for your equation. You can say y equals k over x, or x equals k over y. So notice it really doesn't matter which one is x and which one is y, because it's the same formula. So that's cool. And also x times y is always equal to k, as long as k is not 0. The variable k we refer to as the constant of variation. So in that last example, you see how that, 1,400. Why did I say 1,400? That's 1,500. That 1,500 stayed constant the whole time. This would be our constant of variation. That would be the k, because we need $1,500. So k is the constant of variation. And in this table, here's another example. Notice as the x's increase, the y's decrease, and they do so proportionally. Then you can also, if you multiply every single x times y together, and I'll do that down here, and to get k, 1 times 24 is 24. 2 times 12, 24. 3 times 8, 24. 4 times 6, 24. All of these products are 24. So then on your examples, example 1, you're given a table, and you're asked to help if the table represents an inverse variation. It does if x times y equals k. That's that one formula. So I know an x and a y, if all those products are the same, this is inverse variation. So I've got this third row. Let's go ahead and use it. 1 times 25.5 is 25.5. 2 times 12.75 is 25.5. 3 times 8.5 is 25.5. Then I'll find the other products. So all of these products are the same. So since all of the products are the same, we would say yes, this is an inverse variation because all products x times y are constant. Or in this case, they all equal 25.5. So then example B, same question. So let's check this one out. Let's find all these k values. 6.6 times 3 is 19.8. 5.5 times 5, 27.5. Whoa, those are not the same. So I don't even need to finish this chart to tell you that this is not an inverse variation. Because all the products are not equal. All the products x times y are not constant. Then on example 2, you'll get some experience writing equations for inverse variation. So right now we see that in an inverse variation, x equals 6 and y equals 1/2. What is the equation that represents the inverse variation? So I can give you a couple of steps for this. So the first thing that you'll need to do is you'll need to find k. And remember that k is equal to x times y. So for this, k equals 6 times 1/2, which is 3. So I found k. Step 2, you're going to write an equation. Use k to write an equation. And I can use the equation y equals k over x and substitute in what I know. But whenever you write the equation, you only are going to substitute in the k value. You don't substitute anything else in. So when I write my equation, I'll say y equals, in this scenario, k is 3 over x. And the reason I don't plug in x and y is because those change. Like 6 and 1/2 are the only pair together that multiply to be 3. But if I were to change x to, I don't know, 12, then it would have a different y value. So that the fact that x and y can change, those are called variables. Variable means change. So we leave them x and y so that we can find other x and y pairs later. So then let's look at part B. Part B says, what's the value of y whenever x is 15? So now they've given me a new value for x, and I have to find y. So step 3 is I can sub in the given information, or when I say sub, I mean substitute. Sub in given information to solve for whatever variable you need. So I have the formula y equals 3 over x, and I want to know what is y, so I won't substitute anything in for y whenever x is 15. So I'll substitute in 15 for x. So 3 over 15. 3 over 15 reduces to 1/5. So when x is 15, y should be 1/5. And I can check to see if I'm right. Is 15 times 3 times 1/5 equal to 3? Yes. All right, so I've done this correctly. Next, here we have a word problem. But in this word problem, they're telling me that I have inverse variation already because it says it varies inversely. So this varies inversely is a hint to me that at some point I'm going to be able to use this formula y equals k over x. So let's see. It tells me the amount of time it takes for a cube to melt varies inversely to the air temperature in degrees. So let's let x equal the first variable, or the amount of time it takes for ice cube to melt. Amount of time it takes cube to melt. And we're going to let y equal the air temperature. At 20 degrees Celsius, the ice will melt in 20 minutes. So they're saying when y, because that's the air temperature, equals 20, x equals 20. How long will it take the ice to melt if the temperature is 30 degrees Celsius? Actually, let's make this problem a little more interesting, because then that right now x and y multiplied together is 1. That's not very interesting. Let's change it up. So change your problem in your workbook. Instead of seeing a 20 degrees Celsius, well, I think in your workbook it says 70. So this says 70. It also says Fahrenheit. And also in your workbook, it says the ice will melt in 20 minutes. Let's say 85 degrees Fahrenheit. So the printed version is actually more interesting. Okay, so we'll keep the variables. It just changes the values of x and y. Okay, so when temperature is y, so when y equals 70, x equals 20. So if y is 70 and x is 20, then my constant of variation is going to be 20 times 70, which is 140. And if I write my formula for this situation, I can say that y is always equal to 140 divided by x. Then I can answer the question, how long will it take the ice to melt if the temperature is 85 degrees? So they're asking, what is x when y equals 85? So I'm going to take this formula, I'm going to substitute in 85 for y. Let's see, I've got 85 equals 140 over x. If I multiply both sides by x, I'll get 85x equals 140. Divide both sides by the 85, and x is 140 over 85, which is equal to approximately 1.647 minutes. So if the temperature is 85 degrees, it's going to take about a little more than a minute and a half to melt it. So in example 4, I do want you to change the problem in your workbook to change it to be y equals 1 over x. Y equals 1 over x is the parent reciprocal function. So we're going to graph that. And so just like, y equals x squared was our parent quadratic function, now we have a whole new family of functions called the reciprocal function, and its parent is y equals 1 over x. Now, this looks very familiar to inverse variation because it's got the same setup, y equals k over x, but instead of k being any other number, k in this case is 1. So we have our parent reciprocal function. We are going to graph it. And the way I'm going to graph it is I'm going to make a table of values, and we'll see what happens there. Okay, so I've got this table of values. I've picked some values for x just because I know which values to pick. But once you see the parent function, we'll go from there. But I'm just go with this. Just go with this. Okay, so if x is -3, y would be 1 divided by -3, -1/3. So when I go to graph this, I'm going to try to guess -1/3 is about right there. When x is -2, y would be -1/2. So -2, -1/2 is about right there. When x is -1, y would be 1 divided by -1, which is also -1. So right here. When x is 0, y would be 1 divided by 0, and that is undefined. And we'll fill out the rest. 1 divided by 1 is 1. We'll come back to that undefined part a little bit. 1 divided by 2 is 1/2. 1 divided by 3 is 1/3. And I kind of see a pattern, but I'm not. I need a little bit more information. 1 divided by 4 is 1/4. 1 divided by 5 is 1/5. I'm getting really close. In fact, I'm getting so close to the x-axis it looks like I'm touching 1/6, 1/8, 1/9, but I'm not actually touching the x-axis. I'm getting really, really close. Like if I were to zoom in right around here, you would see a little bit of space in between. Same thing happens on the left side. We get really close to the x-axis, but we don't actually touch it. Okay, so I can tell that my graph does something like this. really close. Keep in mind, it looks like it's touching, but it's not touching the x-axis because I haven't divided and gotten 0 yet. What's happening right here? So let's pick an x value of 1/2. If x is 1/2, y would be 1 divided by 1/2, which is 2. So when x is 1/2, y would be 2. If x is 1/3, y would be 1 divided by 1/3, which is 3. So right here. So we see this, you'll see this pattern start to happen. Okay, get really close to the y-axis, but we're not actually touching it. And it happens the same way going in the negative values as well. So the actual graph of this, the parent function, looks like this. And I'm kind of wobbly because I did this by hand, but then if we also look at the graph on Desmos, we get a little bit better of a picture. You see how the graph, like as I zoom out, looks like it's going to touch the y-axis, but it actually doesn't. There's still a space, and you can see those y values are like 0.064, though it's not quite 0, even though it's really close. And then the same happens on the left. And then we also have vertically that's happening too. Now, when I zoom out, it looks like it's touching the y-axis, but then when I zoom in, the graph just approaches the x-axis. It doesn't actually touch it. Notice those x values aren't quite 0, even though they're getting really close. So that x-axis and the y-axis are what we call, for this graph, they're what we call asymptotes. We have a vertical asymptote and we have a horizontal asymptote. And we denote asymptotes with dotted lines. So let me put some dotted lines on here. So we have a vertical asymptote, and you spell asymptote asymptote at the equation x equals 0, and then we have a horizontal asymptote at the equation y equals 0. So y equals 0 is the horizontal line, x equals 0 is the vertical line. I know it feels kind of weird that y equals 0 is the equation for the x-axis, but that just, y equals 0 is saying that all the y coordinates are 0, and x equals 0, all the x coordinates are 0. But anyway, an asymptote is a line that the graph approaches but does not touch. Is there anything else? We just have to graph it. Now, for equations such as this one that does not involve a lot of parameters, graphing by hand makes sense. As you encounter more complex equations, it might be appropriate to use technology to graph, but we can take this parent function and we can also do some transformation works with it as well. So let's see what's happening with example 5. So example 5, we're going to graph 1 over x plus 2 minus 4, and we'll look at the equations of the asymptotes. But first, we need to talk about transformations. So let's view the full screen. So for transformations, all year we have been shifting things up, down, left, right, and so on. So, but if you have a reciprocal function with the parent function being y equals 1 over x, so that's the parent function for all our reciprocal functions, the formula for transformations is y equals a over x minus h plus k. Now h is the horizontal shift. Now before, you're used to seeing h inside parentheses. H is still in parentheses, it's just the fraction bar acts like parentheses. So x minus h. So if you see a negative h in the equation, then that means you're going to shift to the right. If you see a positive h, you're going to shift to the left. The k is the vertical shift. So if you see plus k, you'll shift up. minus k, shift down. And then A is going to be the vertical stretch. And if you see a negative value for A, or if there's a negative in front of the entire fraction, that is a reflection across the x-axis. So then here I look at the equation and I see that there's going to be a shift. Let's see, plus 2 would be a shift to the left 2 and then down 4. So when I go to graph this, I'm going to start with my parent function and then I'll shift it left 2 and down 4. So let me put the parent function on there first. Okay, so I'm going to shift everything. Now when I graph the parent function, I really just make sure I graph the point 1, 1 and negative 1, 1, and then 1 point on each side of it. So everything is going to shift to the left 2. Everything, including the asymptotes, left 2 and down 4. And so here is the graph of g of x. So this is g of x. So I need to know what are the equations of the asymptotes. Okay, so let's see. The asymptote is the horizontal asymptote. Where do I want to write this? Horizontal asymptote is at the equation y equals whatever this number is right here. 1, 2, 3, 4, negative 4. There's a vertical asymptote. Oh, can't spell. Vertical asymptote at x equals negative 2, because it's right here, negative 1, negative 2. And also, if you look in the equation, see that 2 right there, the opposite of that, negative 2, negative 4, negative 4, it's always going to be like that. So the k is going to tell you your horizontal asymptote. The h, you take the opposite of it, it'll tell you your vertical asymptote. What are the domain and the range? Okay, so here, I need to know the domain and the range. So for domain, my graph starts all the way going forever and ever to the left, negative infinity. And it goes forever and ever to the right. So you would think positive infinity, but it skips this asymptote. So there's one place that this graph does not exist. It goes, so it starts here, it goes down, and then it skips over the asymptote and continues. So I would say that the domain is from negative infinity on the right until I get to the x, to this vertical asymptote, negative 2. And then from x equals negative 2 until infinity. So this graph, negative infinity to negative 2, and then negative 2 to infinity. The range is going to be similar. You'll just give me y values. So the range negative infinity until I get to the horizontal asymptote, so negative infinity until I get to negative 4. And then the y values continue from negative 4 until infinity. The fact that I use parentheses here, see how I have negative 4, negative 4, negative 2, negative 2, indicate that I skip over that number. So I think that should be all for this lesson. So have a great day and let me know if you need anything. Good luck on this, and I'll see you guys soon.